Sketch the graph of the function f of x equals x plus 1, the quantity squared, times x minus 3 over x plus 3, the quantity squared, times x minus 2. The first step in graphing the rational function is to factor the numerator and the denominator. In this case, the factor forms are already given to us. The next step is to find any intercept. This includes the x-intercepts and the y-intercept. To find the y-intercept, we set x equals 0 or replace x equal to 0 and evaluate f of 0. Meaning we just simply substitute 0 into where x is in the equation. 0 plus 1 squared, 0 minus 3, 0 plus 3 squared, and 0 minus 2. 0 plus 1 squared is 1 squared, 1 squared is 1, times 0 minus 3 is negative 3, over 0 plus 3, the quantity squared is 3 squared, and 0 minus 2 is negative 2. And so this is negative 3 over 3 squared times negative 2. 3 canceled out, one factor of 3 in the denominator, and the negative divided by the negative is positive, so we end up with 1 over 6 positive. And so the y-intercept is 0, 1 over 6. To find any x-intercept, we set only the numerator equal to 0. In this case, we have x plus 1 squared times x minus 3 being in the numerator and set it equal to 0. This is essentially solving for the polynomial, but it is already in the factor form in this case. This is one of the reasons why we want to factor the numerator and the denominator if it's not already in the factor form. Using the zero product properties, we must have either x plus 1, the quantity squared equal to 0, or x minus 3 equals 0. Each of the factors need to be 0. And so x plus 1 equals 0, x equals negative 1, or x equals 3. And so the x-intercepts are negative 1, 0, and 3, 0. We also notice that at x equals negative 1, we have what we call a double root. There is a multiplicity of 2 in this case, and we need to keep in mind of the multiplicity because that will help us graph the function at that x-intercept. The next step is to check any vertical asymptote. In this case, there is no common factor in the denominator and the numerator, and so we know that the vertical asymptotes will be x equals negative 3 and x equal 2. This is where the denominator equals 0, x plus 3, the quantity squared, times x minus 2 is the denominator, set equal to 0, and we see that x equals negative 3 and x equal 2. Just because the denominator is 0 doesn't mean that it is a vertical asymptote right away. We still need to check to see if there is any common factor in the numerator. If there is a common factor in both numerator and the denominator, then we won't have the vertical asymptote. In those cases, we will have a whole instead. In this case, there's no factor x plus 3 in the numerator, and there's no factor of x minus 2 in the numerator. And so we know that the vertical asymptotes are x equals negative 3 and x equal 2. If we want, we can go one step further and check to see as x go to negative 3 either from the left or from the right, we need y or the function f of x to go to either positive or negative infinity for it to have a vertical asymptote, or as x go to 2 either from the left or the right, we need to check that the function is approaching either positive or negative infinity. And that is how we know for sure that there are vertical asymptotes. Next, we check for horizontal asymptote. If we were to multiply this out, the numerator has a degree of 3, degree of 2 in the first factor, and degree 1 in the second factor. And so the degree of the numerator is 3. The degree of the denominator is also 3. And so if the degree in the numerator is the same as the degree in the denominator, then we will have a horizontal asymptote y equals at the ratio of the leading coefficients. If we were to take x plus 1 squared and expand it and multiply x, the leading terms will be x cubed. And in the denominator, if we were to expand x plus 3 squared times x minus 2, the leading term will also be x cubed. And so the horizontal asymptote is the leading coefficient in the numerator, 1, over the leading coefficient in the denominator, 1. And so we have one horizontal asymptote, y equals 1. Now this trick only works if the degree in both numerator and denominators are the same. Armed with these information, we will sketch the graph of the function f of x. Ideally, the more points we plot, the better the graph will look. The y-intercept is 0, 1 over 6, and so we plot the point 0, 1 over 6. The x-intercepts are negative 1, 0, and 3, 0. We have the vertical asymptote at x equals negative 3. Remember that the vertical asymptotes are the help lines only. They will not show up in the graphing calculator. We use the dotted lines to draw any asymptotes. The first asymptote is x equals negative 3, and the second vertical asymptote is x equals 2. The graph of the function f of x cannot cross the vertical asymptote. The horizontal asymptote is y equals 1. We would put the line y equals 1 on the graph as well using the dotted line. At this point, we want to check the sign in each interval separated by the vertical asymptotes and the zeros. To do that, we will simply draw the number line and partition this number line from negative infinity to infinity using any vertical asymptotes and any x-intercepts. The vertical asymptotes are negative 3 and x equals 2. The x-intercepts are negative 1 and 3. Picking a number on the interval negative infinity to negative 3, negative 4, for example, and plugged it into the function. The function is f of x in factor form, x plus 1 squared times x minus 3 over x plus 3, the quantity squared, times x minus 2. And so to check the sign in the first interval from negative infinity to negative 3, we use negative 4 for instance. Any number will work. Negative 4 plus 1 squared is positive. Negative 4 minus 3 is negative. And so in the numerator, we have a positive times a negative. And then negative 4 plus 3, the quantity squared is positive. And negative 4 minus 2 is negative. The numerator is a product of a positive and a negative, so it is negative. The denominator is the product of a positive and a negative, so it is negative. And negative over negative is a positive. And so we know that the graph will be above the x-axis from negative infinity to negative 3. From negative 3 to negative 1, we pick a number in between. Any number, negative 2 will work. And we plugged it in. This time, we don't really need to check any factor with the squared because it is already positive. And so if we plug in negative 2 into x in the factor x minus 3, negative 2 minus 3 is negative, and negative 2 minus 2 is negative, and a negative over negative is therefore positive, And so we know that the graph will be above the x-axis from -3 to -1. From -1 to 2, we pick any number, and we see that we can plug in 0. And so the graph, when we plug in 0, it is positive because we did it earlier. When we found the y-intercept, we plug in x equals 0, and we saw that it was 1/6, which is positive. For the next interval from 2 to 3, pick any number, 2.5 for example, and we plugged it in. 2.5 minus 3 is negative, 2.5 minus 2 is positive, and so a negative over a positive is a negative, and so the graph will be below the x-axis from 2 to 3. And then for the last interval 3 to infinity, we pick any number, 100. 100 minus 3 over 100 minus 2 will be positive. And again, for any factor that is squared, we don't need to check the sign because we know that it is positive. From negative infinity to -3, the graph has to be positive above the x-axis, and also when we graph the function, the graph should stay close to the horizontal asymptote all the way on the left, and the graph should stay close to the vertical asymptote when it hits the vertical asymptote. And so on the left hand side of -3, we would graph this piece. The arrows will not be on the graph on a graphing calculator, but we added them for emphasis. From -3 to -1 and then -1 to 2, the graph is above the x-axis. And we notice that at the 0, x equals -1, there is a multiplicity of 2. And so the graph would look like a parabola when it hits x equals -1. We still need to stay close to the vertical asymptote on the right-hand side of -3. The graph keeps going to the right and it needs to hit the y-intercept. And when it approaches the second vertical asymptote, it needs to stay close to the vertical asymptote, and it increases without bound because it is positive in the interval -1 to 2. And so we would connect the x-intercept at -1, 0 with the y-intercept, and the graph would go up and stay close to the vertical asymptote. From -2 to 3, the graph is negative, and from 3 to infinity, the graph is positive above the x-axis, and it stays close to the horizontal asymptote. The vertical and the horizontal asymptotes are there so that they help us to sketch the graph. The graph needs to stay close to the horizontal asymptote from the left and the right. The graph needs to increase or decrease without bounds near the vertical asymptote. That is why we want to determine whether the function is positive or negative above or below the x-axis so that we know which direction near the vertical asymptote the graph is going.